So since we've understood the basic introduction to operating systems, our first major chapter is called as process management. Here we'll talk about processes, programs, and how the operating system manages these processes. This is one of the big chunks of operating system itself. If you think about it, this is one of the larger chapters where we learn a lot of very, very interesting and exciting concepts, right? Your first question should be, what is a process? Okay, so we have been talking about program. We know what a program is, right? How is a process different from a program? So let's think about it, right? What is a program? You write a program, let's say you write a program in C file. You store it on your disk in a .c file. So for example, if I write some test.c, right? So this is what a program is. A program can be compiled and you get a machine level language code, right? You could compile this. You could compile this and you can get an executable code like a.out, right? This is your executable code, but this is still a program. This is not yet a process. What is a process? Let me show you the example. Okay. So if I show you this, look at this. Each of these is a process. Okay. So each of them have a process ID. I've been showing you this, right? Again, this is the view on a Mac. This is called the activity monitor. All the processes that are currently running are there in this window. If you are using Windows, you can also see all the processes that are running by typing or by pressing Ctrl-Alt-Delete and going to the task manager, right? Again, all the processes are visible here. So what is a process? In a nutshell, if you want to, again, there are multiple ways of defining it. I think the most simple way is a process is a program under execution. It is basically a program under execution while it is being executed, under execution, right? So if you think about it, your program is actually stored in your secondary storage. Your program, after even it's compiled, where is this stored? This is stored on disk or secondary storage, mostly your hard disk or your solid state drive, etc. A process, on the other hand, is a program under execution with some resources, and it's a program under execution which is stored in the main memory or RAM, right? With resources allocated to it. With resources allocated to it. With resources allocated to it. Okay, that's very, very important. Again, going back to this view, look at this. If you take any process here, there is some CPU resources it's using. There is some CPU, there are a bunch of threads. There is memory associated with each of these processes, right? There is some network IO associated with each of these processes. Network IO basically means the data that is being transferred through my Wi-Fi here, right? So in a nutshell, a process is a program under execution which is present in the main memory or RAM. That's very, very important, right? So it is actually present in the RAM or main memory. It has some resources allocated to it. These resources could be CPU, these resources could be RAM, these resources could be IO devices. It could be anything, right? At the end of the day, that's the fundamental difference between a program and a process. But remember that a program could create multiple processes, right? For example, we saw the fork example, right? We saw the fork example in the previous videos. Look at this. This is a program. This is one program. But this program created two processes. This is one process. With fork, we created another process here, right? So a single program could create multiple processes using functionality like fork in Unix boxes or the equivalent stuff. For example, we have also seen that if you're using Windows, you could use this function called as spawn to spawn or to fork or to create new processes, right? So in a nutshell, if you think about it, a program is what you write, either it's in a high level language or it's a machine level language. But a process is when you take that program, when you start executing it by placing this in the RAM with resources allocated to it. Okay, this is one way of looking at it. There is another way of looking at it, which is a process is basically a unit of execution. It is something, it is basically a chunk of instructions, okay, or a unit. It's also referred to as a unit of execution. Again, depending on which book, which blog, which article you read, people define it differently, right? But in a nutshell, it is basically a program which is being executed right now. Okay, that's what it is. Very, very importantly. Some people also called program passive, process active. Why is it so? A program is a passive entity because it is not being executed. It is sitting on your disk. while a process is said to be an active entity because this process is being executed right now, right? As I told you, depending on which textbook you read, there are different ways of defining it, right? But the best or my favorite definition is a program under execution in RAM, which is located in the RAM, while a program actually resides on the disk with resources allocated to it. That's one of the simplest ways of understanding it, right? So now let's learn some basics of process. We'll learn lots of interesting aspects of process in this chapter in detail, in lots of detail, okay? How does a process look in memory? So because we said a process resides in the RAM or in main memory. So whenever I say main memory or RAM, main memory, it means RAM, right? Whenever we say secondary memory, it means disk. Secondary memory, it means disk or pen drives or your solid state drives, etc. This is a standard terminology that is used, okay? How does a process look? How does a process sit in the memory? How does it look like, right? There are, broadly speaking, there are 4 chunks corresponding to, again, imagine that this whole thing is my RAM. Within my RAM, my process looks like this. It has 4 chunks. First, obviously, is the instructions. This is the actual instructions that are there in my executable code. Look at this. If this is my executable code, at the end of the day, executable code is a sequence of machine level instructions, right? And the instructions here are basically your machine level language code of what is to be executed. That's what, again, a process has multiple things, right? So instructions is one aspect of it. The second aspect of it is called the static data. Okay, here static, by which I mean it's called the static data. And what is a static data? Again, remember, when I write my program, I'll have some variables and constants that I have assigned statically, not dynamically. Again, there is static data and there is dynamic data. Dynamic data is what I allocate using, for example, in C, if I use malloc or calloc, right? This is called dynamic allocation of memory, if you recall. Again, we have covered this in lots of detail in C programming, right? So if you dynamically allocate memory, that's called as dynamic data store. Static data store is all the data. Because why is it called static data? Because if you look at my program, look at this program. I compiled the program, I have an executable, right? Before the program starts executing itself at the load time. So there is something called as a load time of a program. Okay, before a program gets executed, all of its instructions, everything gets loaded into the memory. Again, this is within the RAM itself. This is the structure of the process in the RAM or main memory. When it gets loaded, because we can easily determine how many variables are stored here or how many variables are created, how much space is needed for each variable, how many constants are there, how much space is needed for it. All that is statically assigned. This memory is assigned at load time, not at runtime. While the dynamic memory, because we don't know how much dynamic memory is needed, right? So this dynamic memory is allocated at runtime while the program or the process is being executed. The static one is allocated at load time. So all these variables, all these constants, the memory for them, again, this is all in the memory. Okay. Then the fourth part is called the runtime stack. Again, we have studied about runtime stack when we learned about recursion. Okay. So what does the runtime stack do? The runtime stack keeps track of all the recursion and function calls. The recursion, function calls, right? And any returns from the functions, all of that stuff. Again, we have discussed about the runtime stack, which we use for recursive function calls or in general function calls and stuff like that. We have discussed this in data structures algorithms on how this works, especially in the case of recursion. Okay. So again, runtime stack itself consists of lots of pieces, like what function is being called, what is the return type, what is the value that I'm passing. The details of it, we have discussed it in data structures algorithms, where we covered it, especially in lots of detail in a topic called recursion. Okay. But broadly speaking, this is what a process looks like in the memory or in the RAM. Again, very often this static data is called as stack space. And this dynamic is also called as the heap space of the process. Okay. So this dynamic memory is called the heap space of the process. The static is called the stack. There is a runtime stack. Please don't get confused with the runtime stack and the static data stack. There are two stacks here. Okay. So this is how a process looks like in the memory, right? Because at the end, what did we say? A process is a program under execution in the RAM. This is how it looks like. Again, this is a simplified diagram, but again, we'll go into more and more details as we progress through it. Okay. Then there are a bunch of operations that we perform on a process. Okay. This is very, very important. Okay. Again, this is also a broad categorization. When we learn about the life cycle of a process, we'll learn much more details about it. Okay. First, let me give you a high level overview of all the operations that we perform. First, we create a process. Okay. Well, what do you mean by when you create a process? When we create a process, we allocate resources that are required. So when we create, we allocate resources. When we create a process, we allocate resources. For example, when we create a process, what do? We take the executable code, we place it in the memory, we place all the instructions, we allocate some space for static data, we also allocate some space for dynamic data, we also initialize the runtime stack. Which means now look at this, we are allocating space in the RAM for this program to be executed. So while creating, we are allocating resources. Resources could be anything. Okay, resources could be RAM, resources could be CPU resources could be IO resources, whatever we have. Right? So allocating resources is what we do when we create a process. Okay. Then we schedule a process. Again, the scheduling of the process, all of these tasks are done by the operating system. Look at this. All of these tasks are managed by the operating system itself. Okay. In most modern operating systems. By scheduling, look at this. At any point, there could be hundreds of processes that are running. For example, look at this. In this case, look at this. I have hundreds of processes running here. I have literally hundreds of processes that are running here. There are tons of processes. Some of them are operating system process, some of them user process, tons of stuff. Okay. So look at this. There are some processes with root user. Okay. Look at this. Root user. Root user basically means the operating system itself is running them. Okay. Or the administrator of this system is running them. Okay. So there are hundreds of processes running. Now, obviously, which process should be scheduled now, or which process should be allocated a resource, okay, is something that the operating system decides. For example, should we now give the CPU as a resource? Again, scheduling can happen on CPUs. CPU is one of the most important resources, right? So it could be on IO device scheduling. It could be on any device. It could be on any of the resources. For example, imagine if I have 100 processes. Which process should be given the CPU now? Which process should not be given the CPU now? How are those decisions made? Again, we'll learn about all of them in process management chapter itself. So scheduling each process on which resource it should be given, especially CPU resources, is something that the operating system has to decide. So operating system creates a process. It also schedules a process. There is also blockage that happens, right? And blockage could happen because of multiple reasons. Okay. One thing is there could be an IO call. We have talked about blockage, right? So in blockage, what happens? For example, imagine I have a program. I executed, let's say I have a program. I executed a few lines. Here I need input from the keyboard. Then this process is blocked now. Okay, because it is expecting input from the keyboard, because till the time it arrives, it can't start executing the next few lines. Okay, so blocks could be because of input output calls, it could be because of input output requests, or it could be because of system calls, right? It could be because of system calls. Maybe I called a fork. For example, if there is fork here, then what happens? The control goes from this process to the operating system, because the operating system has to create a new process. At that time, this process is blocked enough. This process can't progress till the time the OS says, okay, I've created a process, go back and start doing whatever you want, right? So a process can be forced to be blocked either because of input output like keyboard, etc., or system calls. There's a very interesting aspect called as suspension, or suspending a operation. Suspending a process, the suspend operation of a process. This is very interesting. Look at this. At the end of the day, your RAM is limited, right? Look at this. Imagine this is my whole RAM. Your RAM will have, let's say, one process P1 here, one process P2 here. It has some process P3 here. And suppose there are hundreds of processes, which is very common, as I just showed you. If there are too many processes that there is no space for me to hold, suppose let's assume this whole thing is filled. let's assume this whole thing is filled by many processes. Okay, many processes have filled it. Now I want to introduce, I want to create one more process now. There is no space. What should I do? Whatever process is not critical right now, or whatever process is blocked, again we'll discuss about it in detail. Whatever process is not important, I will remove it from the RAM itself. Okay, that's what is called suspension. Suspending a process basically means remove whatever is there in the RAM, store it temporarily in the disk. On the disk, again, if you think about this whole thing as a disk, there is a special space often referred to as a swap space. Again, swap space is a terminology that you encounter on Unix systems like Linux, Mac, etc. Right? So what happens here is whatever, look at this, I want to create one more process, right? I want to create one more process, but I don't have space in the RAM. So what do? I take a process, look at this, I take a process which is not very important to be, which is not currently very critical to be placed in my RAM. I move it out, I swap it out. Suspension basically means swap out. Swap out basically means remove it. Swap out from RAM to disk temporarily. To disk temporarily. To disk temporarily. Again, when I have some space in my RAM left later on, I'll bring my process back to my RAM and start executing it. So there are a couple of types of suspension and stages of suspension that we'll talk about in the next video. But suspension is a very important thing because my RAM is also limited, right? I can't have thousands of processes. I don't have unlimited RAM. I have a limited RAM, which means I should have this scheme wherein if the RAM is fully filled and I want to run something very important, then I need to be able to suspend this process and swap it out from the RAM to the disk temporarily. Then there is this thing called resume. So resume basically means once I'm blocked on something, resume means start resuming it, as the name says. Start re-executing it. Okay. Or resume basically means start scheduling it again for some resources, like start scheduling it for resources like CPU to be executed again. Terminate basically means all my instructions are over. You're done with what we have. Look at this. At the end of the day, my process has a bunch of instructions. Once I've executed the last instructions, I can terminate this process because I don't have anything else left to do. Right? So these are all the key operations. Again, we'll discuss about operations in lots of detail when we look at the life cycle of a process. But broadly speaking, these are the things that an operating system manages for a process. It creates, it schedules it, it enables it to be blocked, it suspends it whenever required, it resumes after suspension and blocking, it also terminates once everything is over. In terminate stage, what does it do? It deallocates all the memory that was there, that was initially assigned for it. All the resources and everything that was initially assigned to the process will be deallocated at the time of termination. Okay, very simple. Again, there are multiple attributes associated with a process. Okay, so for example, we talked about process identification like PID. Right, look at this. Again, let's go back to this. Let's go back to the activity monitor on my Mac. Look at this. Every process has a PID assigned to it. Right, there is a process ID, which is a unique ID. Again, the attributes associated with each process differs from OS to OS. Okay, it changes. The attributes that are associated with a process changes from OS to OS. Again, different OS are implemented differently. Changes from OS to OS. But broadly speaking, these are the types of attributes that we typically store. The process identification, this is often referred to as process ID or PID on most Unix-based systems. Okay, again, you also hear terms like PGID or just ID in some operating systems, etc. Okay, but this is a unique way to identify a process. Similarly, there are also CPU-related attributes of a process. For example, look at program counter itself. We discussed about program counter, right? What does program counter have? Program counter actually has, suppose imagine these are all the instructions corresponding to the process that is being currently executed, right? The program counter is a pointer. It stores the address of the next instruction to be executed. Why is it a CPU related resource? Because program counter helps the CPU understand what is to be executed next, right? So there are CPU related attributes of a process like program counter, there are general purpose registers. there are GPRs or general purpose registers associated with this process. Okay, because I could store some data related to these processes in the registers which are part of the CPU. Remember, your program counter, your general purpose registers are all part of CPU, right? But these are assigned to a process while it's being executed, right? Similarly, there is something called as CPU priority that we will learn of little later. There is something called as priority states. Some processes will have higher priority than other processes. Let me give you an example from the Android world, okay? Because I've given you a lot of examples from the Mac and the Linux world. Let me give you an example from the Android world. So imagine I'm browsing a page on my Android phone, right? Suppose there is a call. Somebody is making a call to me. What happens? That call overtakes the whole screen. So the call, so suppose if somebody makes a call to me, okay, I'm reading something on my, let's say, Chrome browser on Android. Okay, so this is my browser, I'm reading it. So what happens? As soon as I get a call, the call has a higher priority. So again, this is a process. Getting a call is nothing but a software process. Me reading something on the browser is also a process that is being executed right now, right? The call has a higher priority. Okay, hence what happens? This call takes over and takes all the resources it needs. What resources does a call require? It obviously requires the resources of the CPU, because whatever I'm speaking has to be transmitted, right? The call requires a CPU. The call requires access of the speaker, right? The call requires access of the microphone. All these are hardware resources, right? The call requires some space in the memory. The call requires my what do you call it? Not my Wi-Fi, my telephone bandwidth, right? Whatever is the communication channel, right? So it requires the communication channel. It requires the communication channel or protocol that is required to transmit my audio to the other side, right? So call as a process has a much higher priority than me reading something on the browser. So the call takes over. So for every process, there is a priority state. Like this is like hypercritical priority. As soon as it comes, we have to make it work, because people don't want to wait. People are okay if you disturb them from when they're reading something on a browser with a call, right? So here the call process, which requires all these resources, has a higher priority than the browser process. Okay, that's what is called priority states. Again, priority of processes is a very important topic that we'll discuss in lots of detail in this chapter, right? Similarly, every process has some memory. There also, of course, every process has some memory allocated to it, right? Now, there are also memory attributes associated with a process. For example, memory limits, right? Some memory limits, right? For example, I can't give infinite memory to a process. So I'll say, okay, I'll only allocate this much memory for your dynamic allocation. I'll only allocate this much memory for your runtime stack, right? Sometimes you get this error, right? That I've run out of space. What does that mean? Because every process is assigned some limited space. If I keep using malloc and calloc, and if I keep creating space, what happens? The memory assigned to this process could run out, right? So there are memory related attributes of a process like memory limits. Okay, there are other concepts that we will learn of called page tables, etc. Don't worry about these concepts. We will learn about them when we look at memory management. Memory management is one of the big topics of operating systems. There we'll understand what a page table and things are. Okay, there are also file related attributes of a process. Which all file IDs? Okay, this all the file IDs and file pointers that I have currently opened, right? Which files do I have access to right now, right? All these are file related attributes corresponding to a process. There are also IO related, because file is also one type of IO device. Files are stored on a disk. Disk is an IO device. There could be other IO devices like your keyboard, right? Suppose, for example, I'm executing a program. Whatever I type in the keyboard, does it now go to this process or some other process? That's important, right? So you could have all the devices. These are often referred to as open devices. All the devices to whom this process has an access. All of that information is stored in IO related attributes. There are also some protection related attributes. For example, which mode is this process running in? We discussed about it, right? We discussed about process status word, right? So there are some protection related stuff here. Things like whether it's running in kernel mode or user mode and things like that. Similarly, does this process have permission to run in, for example, does this process have permission to open some files? Okay, so all of these are attributes associated with a process. Okay, I hope you got a good sense of what these are, but remember, they change from operating system to operating system. Right? But these are broadly some of the key ideas. Now, what happens is all these attributes are typically stored in a table. Okay, so this is often called as the PCB, which stands for process control block, which is called the process control block. Okay, so every process has a PCB. Every process has a PCB. Every process has a PCB. Think of PCB as a data structure. You can also, many people call this as PCB data structure. PCB is a data structure which stores all of these attributes corresponding to a single process. Okay, you could think of it as a big lookup table. Okay, where it could have, okay, what is my PID? Okay, this is my PID now. PID equals to this. Okay, then it could say what is a program counter now? Okay, what are the general purpose registers that I have access to? Okay, what is my mode? Okay, so think of it as a big table corresponding to each process. Each process has a process control block. Process control block tells us everything about the process, whether it's a process ID, what types of attributes does it have corresponding to CPU, memory, file related, IO related, protection related, everything it gives us. Literally, it gives you all the information. Again, PCBs are also called as the context of a process very often. PCBs in some textbooks are also referred to as the context or the environment of a process, right? And remember that every process has a unique PCB corresponding to it. Very simply put, right? So again, what we're discussing here is very, very basics of what a process is, but we'll go into lots of details in this chapter about, again, there are some terms here you may not have understood, like how does priority work? How does, for example, here, how does scheduling work? Right? How does suspension work? We'll look at all of those concepts in the rest of this chapter. This is just the introduction to what is a process, how does a process look in a memory, what are the operations that the operating system performs on a process, and what are the key attributes associated with a process. Okay.